Hello, myself Sushant Mukhopadhyay, faculty member, Electrical Engineering Department, Greater Kolkata College of Engineering and Management. In the last class of Electrical Machine 2, we have discussed the armature winding, uh, how it is being placed in the uh, slots of the AC machine's windings, that is in case of asynchronous machine and as well as synchronous machine. So, and different types of winding, single layer, double layer, etc. Now, today we'll start with the MMF of distributed winding. In the last class, we have discussed what is distributed winding, what is concentrated winding, etc. So, distributed winding is actually it is the total winding of the stator or armature is being distributed in different slots along the periphery of the armature or stator. Most of the cases in AC machines, distributed windings in armature are used for most of the rotating machines. So, due to flow of current in different coils, which form the armature winding, a magnetic field is of course produced, having the same number of poles as the field winding. So, the magnetic fields pattern, along with air gap periphery, this is set up by this distributed winding, is dependent on some factors. So these are MMF produced in a distributed winding depends on winding arrangement, nature of the current flowing through the winding, and definitely the configuration of the magnetic circuit. Once again, I am repeating this MMF produced in distributed windings depends on some say factors or some parameters or some basic things, that is winding arrangement, how the winding is being arranged, whether it is arranged in lap or in a wave pattern, say nature of the current flowing through the winding, whether it's AC or DC, and of course the configuration of the magnetic circuit. So the distribution of air gap flux in the machine help us to determine the wave and magnitude of the generated EMF, and of course the electrical torque. So this distribution of air gap flux in the air gap of the machine is having a very important role. So it help us to determine the wave and magnitude of the EMF generated, and of course the electrical torque. Now this MMF production by distributed winding in the slots along the air gap periphery will be discussed first. Then we'll go for the other topics of this MMF distribution. Let us suppose this figure A, this figure. So this is that each slot has 6 conductors, where each conductor carries the current I. See, this is slot, this is teeth of a say armature winding. Say in the slots there are say double layer winding, say 6 conductors, top 3, bottom 3, and in this way. So and each conductor carry a current I. So due to traversing path 1, the ampere conductor enclosed becomes 2I, of course. See, this is ampere conductor enclosed 2I, and change of MMF also being shown here in this. This is MMF. This is 2I. Okay, so Um, now, if the paths 2 and 3 are traversed, this is path 1, this is equal to this is path 2, say, for this another 2 conductor, and this is path 3. Okay, so if we traverse this 2 and 3, the ampere conductor becomes then will be how much? So 2i plus 2i for the second part, then it is 4i, and for the third part, so cumulatively it will be 6i. Okay, so it will be increased up to this, and this is 6i. Okay, so now this uh, this figure B. So this is showing the MMF variation which changes linearly from 0 to 6i over the slot width. Now figure C, this one, this shows the simplified form of this. This is the simplified form of figure B, where change of MMF is considered as stepped at the middle of the slot. See, this is the slot, and this is the middle of the slot. It is stepped, okay, and so on. So these are so nicely depicted in this figure. So this is slots. This is the MMF path for first 2 conductors. This is for second 2. That means this is the third. So this is the MMF distribution. So 2i, 4i, 6i. This is simplified form in the step form. So which is taken from the middle of the slots. Okay. So this is the MMF by distributed winding in the slots along the LV. Now we'll come to the second one. This is a full pitch coil. This is a full pitch coil, A dash. Okay. Suppose this is a full pitch coil on the stator for a 2-pole machines. So having uniform aircraft. See, this is stator, this is rotor, this is the end. Okay, so this is a say uniform aircraft. So let's suppose the coil consists of n turns, where each turn carries current I. So direction of the current is shown here. So this is N-cycle cross, and this is N-cycle dot. So if we apply if this is the direction, that means this is going inside the phase, and this is coming upwards. So if we apply the Maxwell's force rule, then it will give you the direction of the MMF path. Okay. Now, so this is stator, magnetic axis of the stator coil. So coil is like this, and this is the axis. Okay. So this is the internal coil, and this is the say current directions. This is the current directions. This is the flux path. Okay, applying the Maxwell force rule. Now, this figure B. This is the developed view. So if you cut stator and you make it flat, so it will be like this. Okay. So this is the current direction. Okay, current direction, and this is the flux path. Here, this is the flux path. Okay. And the following the assumptions are taken to simplify the analysis. Let's say the stator and the rotor iron have much higher permeability compared to air, so that the magnetic flux is offered by the air gap only. The magnetic lines of force cross the air gap radially. You have seen it here. And now if you apply the Ampere's circuitry law, the encircled integration of closed path over H dot dl into the total current. So this is, and total current is how much? So this is the path, total current. This is the air gap, G. So this is, path is G and G. So it is 2G. So 2G H will be equal to n number of turns and I is the current, so Ni. So G is equal to half Ni. So this equation, so the magnetic potential difference across the air gap is half Ni, and this C, figure C, shows the variation of magnetic flux along the air gap periphery, and this magnetic flux leaving the rotor or entering the stator is considered as positive. Okay, this is shown here. So this figure C shows the air gap MMF wave at any instant is rectangular. Okay. MMF wave is any instant is rectangular. Okay. There is no variation of MMF with time and space. So when the current in the coil is direct in nature, if it is alternating in nature, MMF varies with time, not with the space, but that is, it is time variant only. So if we use a Fourier series, the rectangular MMF waveform having magnitude half Ni can be resolved into its fundamental and higher order components. The fundamental components part becomes this. This is the fundamental part, by Ni by 2 cos alpha. And if say this is equal to F1P, then F1P cos alpha. And that F1P is always the along the along with magnetic axis of the coil. When I is the alternating type, the maximum value of F1P becomes F1P equal to 4 by this. So the maximum value of I equal to I max equal to root 2I. Now, if we say about for a P-pole machine, so this will be, in case of it is 2, it will be P. So 4 by 5 this will be. So here in this figure, this C P-pole machines. Okay. Say C full pitched coils in the stator. C full pitched coil. Okay. This, and there are C full pitched coil in the status, and windings are distributed on the status. So let each coil has n turns, and each turn carry a current I. So developed view of this figure will be shown here. Here. Okay. This is the current shift model. So this is the magnetic axis of distribution. Here is a uniform current shift, like this. Okay. So now figure this figure, see this one. So this is the MMF variation of the coil A dash only, which is rectangular waveform. This coil A dash only, rectangular. Then this is the next pair, EB dash, and this is CC dash. So actually, and its magnitude is plus minus half Ni. And 2 and 3 show the MMF variation of the coils BB dash and C dash respectively. So when the individual MMFs are summed up, the combined MMF can be obtained, and figure 634. So this one. Okay, this is the combined MMF, and it will be of say with the left. So combined MMF of the left of the coil is minus 3 by 2 Ni, and its value is in between. It is minus half Ni to plus half Ni between. Once again, I am repeating this discussions of three full pitch coils on the stator. So this is shown three full pitch coil: A dust, one coil; B dust, another coil; and C dust, the third full pitch coil. So, and if we suppose that each coil has n turns and carry a current I, so then this figure B, this is the path. If we take it as a current sheet, let's say this is the original one. This is the magnetic axis of the. This is the coil. So this is the magnetic axis of the distributed winding. This is the magnetic axis of the uniform current sheet. This is, if you consider it is a current sheet. So this is the direction of the current. This is entering towards the phase, and this is coming out of the phase. So this is the n cycle dot, and this is n cycle cross, and this is the say flux path, MMF path. So if you apply the you stretch your say thumb along the direction of the current path, and say stretch and you move or fold your the rest of the fingers, it will show you the path of the flux or MMF as stated in the Maxwell's Cost-Pull rule. So now if we say figure this figures C1, this is due to coil A dash. This is the flux part. This is due to coil B dash, and this is the third coil CC dash. So this is the flux path, and you are seeing that the variation, of course, is between plus minus Ni for each of the coil or the MMF magnitude. So this is showing this rectangle the waveform. Now, when these individual MMFs are summed up, the combined MMFs can be obtained. This is shown here. This is shown. And this shows that this combined MMF of the left of the coil A is minus 3/2 Ni. This is coil A, minus 3/2 Ni. And its value is minus half Ni between coil sides A and B. So its value between A and B, it is minus half Ni to half Ni, and then from B to C it is plus half Ni. Okay, so half Ni and minus half Ni, it is plus half Ni between coil sides B and C. So the combined value of MMF between coil side C and A dash is how much? Combined value is between C and A dash is C. This is C and this is A dash. This is 3/2 Ni. Okay. So this shows, this figure gives you the complete combined value of MMF. Okay. Here it is. So this picture shows clearly the for a three full pitch coils the air gap MMF distribution as a whole. Okay. Now we'll come to the next topic of discussion, that is winding factor. Before talking about the winding factor, definitely we must have to know what is pitch factor or coil factor and what is distribution factor. Then we get the winding factor, which is nothing but the product of these two factors. This is the pitch factor and distribution factor. So if we denote winding factor is Kw and pitch factor is Kp and distribution factor is Kd, then winding factor will be the product of Kp and Kd. So let us discuss pitch factor and distribution factor. Let us suppose pitch factor in short pitch coil, the induced EMF of two coil side get vectorically added and give resultant EMF of the loop. In short pitch coil, the phase angle between the induced EMF of the two opposite coil side is less than 180 degree, of course, but in full pitch coil, the phase angle between the induced EMF of two coil sides is exactly 180 degree electrical, which is nothing but the whole pitch. So that's why it is called full pitch coil. So resultant EMF of a full pitch coil is just the arithmetic sum of the EMFs induced on both sides of the loop. So we know the vector sum or phasor sum of the two quantities is always less than their arithmetic sum. Therefore, the pitch factor is the measure of resultant EMF of a short pitch coil in comparison with resultant EMF of a full pitch coil. So it must be the ratio of phasor sum of induced EMFs per coil to the arithmetic sum of the induced EMFs per coil. So therefore, it must be less than unity because the numerator is less than the denominator. So let us assume a coil which is short pitched by an angle alpha, okay, and alpha electrical degree. If EMF produced per coil side is E, so then so actually this arithmetic sum of the induced EMF is 2E. That means 2E is the induced voltage across the coil terminals if the coil would have been full pitched. If it is a short pitched and it is the shown here, so this is the angle, this is also as per definition of the pitch factor, so resultant sum of the short pitched coil and divided by the resultant EMF of the short pitched coil divided by resultant EMF of the full pitched coil will give you the pitch factor Kp. So this is the phasor sum of the coil side EMF, and this is the arithmetic sum of the coil side EMFs. So phasor sum is this 2E cos alpha by 2, and the arithmetic sum is 2E, so therefore cos alpha by 2 is the pitch factor. So the flux pitch factor is the fundamental component of EMF, and the flux may have consist of space field harmonics also, which gives rise to corresponding time harmonics in the generated voltage waveform. So a third harmonic component of the flux wave may be imagined as produced by 3 poles as compared to single pole for the fundamental component. So in the view of this, the coding angle for RF harmonic becomes R times the coding angle for the fundamental component and pitch factor. For the RF harmonic, it is so KPR is cos R alpha by 2. So if RF harmonics becomes 0, then it will be cos R alpha by 2 is equal to 0 and alpha by 2 is equal to how much? Say 90 degree. Okay. 90. So if three-phase alternators in three-phase, the harmonic is suppressed by so if for seventh harmonic we consider, then so this coding angle will be coming about 25.7 degree. If it is a fifth harmonic, so it is 36 degree. If it is a third harmonics, it is for it is a 36 for fifth, and for seventh harmonic it is 25.7 degree. Hence, by adopting a suitable coding angle of alpha to 30 degree, you make most optimized design armature winding of alternator. Now come to the point of distribution factor. If all coil sides of any one phase under one pole are bunched in one slot, the winding obtained is known as concentrated winding, and the total EMF induced is equal to the arithmetic sum of the EMFs induced in all the coils of one phase under one pole. So the resultant EMF of the winding is the phasor sum of the induced EMF per coil side, as it is phasor sum. So must be less than the arithmetic sum of these induced EMFs. So resultant EMF would be an arithmetic sum if the winding would have been a concentrated winding, of course. So as per definition of the distribution factor, the measure of resultant EMF of a distributed winding is in compared to concentrated winding. So we express it as the ratio of the phasor sum of EMFs induced in all the coils distributed in some slots under one pole to the arithmetic sum of the EMFs induced. Therefore, distribution factor is EMF induced in the distributed winding by EMF induced in the winding if it be a concentrated one. So that means it comes to phasor sum of the component of EMFs divided by arithmetic sum of the components of EMFs. So if we see here, the pitch factor, distribution factor is always less than unity like pitch factor. So let the number of slots per pole is n, number of slots per pole per phase is n. So in that case, induced EMF per coil side is EC, this one. Angular distribution between the slots is how much? 180 degree by n, the number of slots. Then it is beta that represent the EMFs induced in the different coils of one phase under one pole as AC, DC, DE, AC, CD, DE, etc. and so on. So they are equal in magnitude, but they differ from each other by an angle beta. If we draw the bisectors on AC, CD, DE, F, they would make a common point O. It is shown here. Okay. EMF induced in each coil side E equal to AC equal to 2 OA sine beta by 2. OA sine beta by 2, and the resultant EMF would be AB, and it is represented in the figure, and the resultant EMF will be AB equal to this equal to OA sine beta by 2. Therefore, distribution factor will be phasor sum of the component of EMFs by arithmetic sum. This is the phasor sum, this is arithmetic sum, and it comes to sine m beta by 2 by m sine beta by 2. So m beta is also known as the phase spread in electrical degree. So distribution factor KD is given by the equation is for the fundamental component of EMF. If the flux distribution contains phase harmonics and slot angular pitch beta on the fundamental scale, it becomes R beta for the Rth harmonic component, and thus distribution factor of the Rth harmonic will be like this. So R m beta by 2 is the same sine R beta by 2 here. So therefore winding factor will be this Kw is the product of Kp into Kd. So that is cos alpha by 2 into this is distribution factor sine m beta by 2 by m sine O beta by 2. So like pitch factor, I told you that distribution factor also for different harmonics it will be multiplied by the for Rth harmonic it was R beta, etc. So it will be like this. So that's all about your winding factors. So this is the product of pitch factor and distribution factor, of course. And for AC machine, though full pitch coil will generate generates more EMF, though full pitch coil generate more EMF, but mostly in distributed winding, corded coil or short pitch coils are used because it not only helps the elimination of higher order harmonics. So elimination of higher order harmonics make the MMF or flux profile as well as induced EMF profile much more better. That is sinusoidal more. And not only this, if we sacrifice a little bit of say more generation of EMF, so cost of towards the conductor will also be minimized because the length of the corded coil will be definitely a little bit less than the full pitch coil. So in this way, so corded coil, if we see the overall advantages, then in distributed winding, short pitch coil is mostly used. So that's all about the winding factors and its necessity and how it is being say explained here. So thank you all of you for say patient hearing. Now if you have any queries you ask me or later on you can call me or mail me or WhatsApp me. So thank you all. So that's all for today.